Okay, we're going to start topic 4C. So, okay, so topic 4C is going to take us on the transition from looking at just pure substances and thinking about equilibrium to making mixtures or solutions, and then going from there to solutions that can have reactions taking place. So partial molar quantities are a way of thinking about how different properties change when the composition is changed. So the key idea is that a partial molar quantity is the contribution that a substance makes to the total system. The chemical potential is the partial molar Gibbs energy, we'll see. So partial molar volumes are usually the easiest thing to visualize because it's harder to visualize Gibbs energy. But by thinking about partial molar volumes, you can think about what a partial molar Gibbs energy would be. So the total volume is going to be equal to the number of moles of A that you add. And this thing is the partial molar volume of A. It's actually a derivative. It's how the volume changes with the number of moles of A, holding everything else constant. And that's not necessary, but it helps you think a little bit about the fact that the partial molar volume of A and B aren't constants. And so when we look at this picture, it really helps you think about how some systems are very far from having additive volumes. So you have to look at this diagram. It's really not a very good diagram. This line, actually, I can just redraw it. So the mole fraction of ethanol, and then the partial molar volume of water and ethanol. So the partial molar volume of ethanol is in red, partial molar volume of water I just drew in blue. So notice that the volume changes very differently as the composition changes. So definitely isn't additive that the partial molar volumes are constants over this composition change. So these weird shapes really take into account the fact that when water and ethanol are at certain compositions, their packing is so different that the volume changes in a very, very different way. So that picture shows you that these guys are actually derivatives and they're not constants over the composition, which will be same for a partial molar Gibbs free energy. So go ahead and do this self-test and then come back and listen some more. So it's just making you think about that equation right here. You have the number of moles, you have a partial molar volume, whoops, and how is that going to impact the total volume? So try to do that self-test. So when we talk about the chemical potential is the partial molar volume of Gibbs free energy. So it's how Gibbs free energy changes per mole. So the total Gibbs free energy would be the chemical potential times the number of moles of A, the chemical potential of B times the number of moles of B. So that equation is totally analogous to this one for volume. So volume is replaced with Gibbs free energy. The chemical potential is, as it shows right up here, by definition, just the molar Gibbs free energy. So that's what we're going to be concerned with in our mixture. So we want to, essentially, we want to derive this equation because we want to know how chemical potential changes with the change in pressure. So equation number 3. So in order to derive that, so here's the equation we're trying to derive, how the chemical potential of any one component changes from what its value would be at your standard state pressure to a new pressure. So we want to go back and think about what we learned at the start of this focus, that a change in the molar Gibbs free energy is equal to the molar volume times dP. And so we're going to integrate both sides to try to get a finite change. So that makes this on the left-hand side just the chemical, or the Gibbs free energy at some new pressure minus the Gibbs free energy per mole at their standard state. And on the right-hand side, we're going to integrate. But if we're talking about an ideal gas, so we're going to start by thinking about gases. So for an ideal gas, then the molar volume has to be written as RT over P because it changes with pressure. So when we integrate this, you'll notice again, we're doing the same integral, 1 over x. So we'll get RT ln of P over P naught. And now by definition, these are the molar Gibbs energy. So molar Gibbs energy for the J component at the new pressure versus the molar Gibbs energy at standard state. So those are the chemical potentials. And so we end up with this equation, which is what we wanted to show. So a change in chemical potential with pressure So if we have any old random set of pressures and we want to go from pressure initial to pressure final, then our final state is the chemical potential at a new pressure versus our initial pressure. And when you combine these, what you see is, by remembering that the natural log of x minus the natural log of y is equal to the natural log of x over y. When I take the difference of these two, I can pull the RT out front, and also the mu chemical potential standard state cancels because this minus this is 0. So I just end up with these RT terms, pull the RT out front, look at it again, take advantage of this log rule, and what you end up seeing is that these standard state pressures cancel, and you end up with the change in a chemical potential going from some initial pressure to a final is just RT ln of the pressure of the final state over the initial state. Starting you to think about equilibrium constants. It's a long way off, 2 more sections, but that standard state pressure is always there dividing your pressure. That's why this actually ends up being unitless. So just then taking everything out that I canceled, the change in chemical potential for any substance J is equal to RT ln of what the new pressure is over the old pressure. So stop and do self-test for C.2 on page 139, just uses that equation. Let's do all of that. So now we're going to look at just the very simplest thing that we can do, which go from a pure substance to mixing 2 perfect gases. So we're on a slow process of looking at anything that could be considered a chemical reaction. So we're just going to start out by thinking about how does the Gibbs free energy change if we just mix 2 perfect gases. And it turns out that this is the equation we're going to derive. It's just going to end up to depend on the mole fractions. So if we start out, we'll say the chemical potential of a system of 2 components is equal to the number of moles of one component times its chemical potential, plus the number of moles of the other component times its chemical potential. And if you write those out as the equation we derived, it would be number of moles of A times the chemical potential when it's in the standard state pressure, plus how it changes as you get to a new pressure. And the same thing for B. So if you look at figure 4, just so you understand what we're doing, this picture right here, we're simply going to pull out a barrier from our initial state where they're separated and allow them to mix. And notice that the container stays the same size, so the total pressure stays the same, which will be important. But here we have A and B as separate pure components, and here we're going to have a mixture. So remind ourselves what a mole fraction is. So mole fraction is the moles of A over the total moles. So that would be Na in our equation over N, and that equals the mole fraction. And so when we now write the final state Gibbs free energy, it's going to be the sum of the Gibbs free energy of A and B. And so I can pull out N, and because N times XA equals Na, and just pull it out here, and then also pull out N on this side because N times XB would also equal NB. So this is the chemical potential when they're mixed. So if we take the final minus the initial, that's going to be the delta G for mixing. And so I'm going to take this equation and subtract this one. First thing you'll notice is that these standard state terms go away because Na times mu A standard state is the same as Na times mole fraction times the standard state. So if I'm subtracting this from this, both of those standard state terms will cancel, and I'll just end up with the terms that compare the pressure. So in the final state, my pressure is PA, the partial pressure of A, and partial pressure of B. And in the initial state, each gas was simply at the pressure of the container. So when I just rearrange that, I end up with the equation almost as we want it to be, except that now we can think about two things: that pressure of A is equal to mole fraction of A times the total pressure. That's Dalton's law. And so that would mean pressure of A over total pressure equals mole fraction. So each of these guys can just be replaced with its mole fraction. And then it's also true that the difference in logs we know is equal to the log of the ratio. And so when I take ln of PA over standard state minus ln of the standard state, oops, I've already done that in this equation, then the standard state pressures cancel. So that's how we got to here. So that's how we got from the bottom. That's how we got from this equation, which would have had two terms for A and two terms for B. And by taking advantage of this log relationship, you can end up canceling the standard states and just ending up with the partial pressure of A after it's mixed compared to the pressure A started at, and the partial pressure of B after it's mixed divided by the pressure that you started at, because the standard states will cancel. And so we end up with the equation once we put in the pressure ratio is equal to the mole fraction that we wanted. And you'll notice right away, because mole fraction is always less than 1, that this is always going to be negative. It's always going to be spontaneous to mix two perfect gases, which is something that we already know. It's also true that delta H of mixing is going to be 0 if it's perfect gas, because if the molecules don't interact, then you have no change in energy as they mix or they're separated. And then if you wanted to know the delta G or delta S of mixing, it's going to be delta G equals delta H minus T delta S. Delta H is 0. So delta S of mixing is just going to be delta G of mixing divided by T, and then change the sign. So that's just all the derivation. And then self-test for C.3 just uses that equation. So let's just read that. So the self-test says evaluate the changes in molar Gibbs energy, enthalpy, and entropy when 2 moles of A are mixed with 1 mole of B under the conditions of the problem that was before it. And the only condition we need to know is that it was at 298. So when I do that problem, okay, so I'm going to use my equation. So write that down. The mole fraction of A is 2/3, so it's natural log of 2/3 times 2/3. Mole fraction of B is 1/3, so natural log of 1/3 times 1/3. We have 3 total moles, the gas constant, and 298. So I got delta G of negative 4.73. Delta H is 0 because they're perfect gases. And delta S of mixing, you don't have to go back and redo all that. Just take your delta G, change the sign, divided by 298, and I got 15.9 joules. So the entropy of mixing is positive. And that is all of that section C. Next, we're going to go on to thinking more about solutions and talking about colligative properties before we then go into focus 5, which goes into actual chemical reactions.